Hi. In this presentation I will talk about the specification for the sheeting electronic dice, which corresponds to the first assignment in our compulsory coursework. After watching this presentation, I hope that you will be able to describe the functional specification of the required dice, also to identify the main design tasks and know how to divide them among the group members, and finally know how to start your development work. The functional specification may be summarized in 3 key points that are listed in this slide. The running mode is the normal operating mode. When we initiate the circuit operation, the dice will be in this running mode, where all the 6 possible results will be displayed in sequence. So the LEDs will show result 1, then 2, 3, 4, 5, 6, and then repeat this cycle over and over again. However, the 7 LEDs will be updated so fast that instead of seeing each result in sequence, what we will see is simply the 7 LEDs lighting up at the same time. The second key point in our functional specification is the existence of a stop button that will stop the running mode as soon as we press it and show the current result. The stop button will be one of the push buttons in the Nexus 3 board, and it will keep the e-dice in stop mode while we continue to press it. So if the result that was driven to the LEDs at the moment that we press it, the stop button was, for example, 3, then we will continue to see result 3 while the stop button is pressed, and then revert to the normal running mode as soon as we release the stop button. Finally, the last key point in our functional specification is the existence of these 3 mode switches, which will be used to define the sheeting or no sheeting mode, as we will see in a table that will be presented later on. You should notice that the wiring in the Nexus 3 board defines some basic default assumptions that you should keep in mind. The first of them is that the board LEDs are connected in a common cathode mode, as you can see here on the right of this slide, meaning that to light up an LED, we must drive a logic 1 to the corresponding pin. The second assumption to be followed in our design, if we want to use the LEDs that are already available on the board, as shown here, is that each LED has its own driving pin. You should notice that this is not strictly necessary because some LEDs light up in pairs. Actually, the only LED that lights up alone is the one in the middle here. Apart from this one, the top left always lights up in pair with the bottom right. The top right lights up in pair with the bottom left, and the 2 in the middle also light up at the same time. So 4 pins would be sufficient to drive these 7 LEDs, but because we have this wiring already available, we will simply use 1 pin for each LED. Finally, the third assumption is to consider that all inputs are active high. In the case of the push buttons, as you see here, this is again a result of the wiring on the board. As you can see, since each push button has an associated pull-down resistor that drives a 0 to the corresponding input when the push button is not being pressed. Now, of course, when we push the button, then a 1 will be driven. As for the two position switches, which will be used to define the sheeting mode, we will consider that putting them all to 0, as shown here above, will mean that the sheeting modes are not active. So we may start by building a table that lists the operating modes according to the inputs defined by the stop button and the 3 sheeting mode switches. I have done it partially in this slide so that we will have a common departing point for all the groups. As you see here, if the 3 sheeting modes are set all to 0, and if we are not pressing the stop button, the dice will be rolling, and each of the 6 possible results will be displayed in sequence. In this table, I am also proposing that the all-one combination for the sheeting mode switches is used to define a sheeting mode where result 4 has triple probability. This can be ensured by going through a cycle where each result comes out only once, except for result 4, which comes out 3 times in each cycle. Now, one possibility would be to have a cycle that goes like result 1, then 2, 3, 4, 5, 6, and then again 4, 4, before restarting the cycle at 1. So the probability of hitting result 4 when we press the stop button is triple in this case, since its result will last for the same time, and result 4 happens 3 times for each cycle. The remaining combinations for the sheeting mode switches, as indicated here, will be used to define options where the corresponding value will come out for sure whenever we press the stop button. For example, if the 3 mode switches are set to 0, 1, 0, as shown here, then the result 2 must be displayed whenever we press the stop button. So I leave it as an exercise for you to complete the table in those cases that are yet undefined. We will also need to define the output combinations that must be driven to the LEDs in order to generate each possible result, but this is easy to define, and you can do so by filling in the remaining lines in this table, considering the first line that I give you as an example for result 1. And this is it. I think that you have all that you need to start your work, and I leave you some recommendations in this final slide, where I have listed the main tasks that need to be carried out to develop a working solution. It may be useful to divide these tasks among yourselves and to allocate responsibilities for who should lead each task. Please bear in mind that they have different complexity levels, and indeed the second one, addressing the state diagram or ASM chart, will surely benefit from a discussion involving everyone in the group, because this is the most complex task in this assignment. Well, as a general rule of thumb, you should try to complete the ASM chart and the function tables by the end of the first week, and then leave the VHDL coding and the implementation for the second week. Thanks for your attention.